Hello! So, in this video, we're going to very much be talking about why this method of an integrating factor works so well. Okay, essentially, what we're going to do is, if you remember, we have an equation, first order linear differential equation that looks like that. Okay, and essentially, what we do is we introduce a new function. Okay, so mu, and when we introduce this new function and multiply this new function through that equation, then effectively we just get rid of that middle term there, okay? And the question is, why do we get rid of that middle term? So we're going to look at it in more detail. So, I've got my solution, my y, which satisfies this equation, is also going to be dependent on x, because x is my variable which goes on here. Sorry, this should be x, yeah. So, yeah, it's all going to be on x. Okay, so the way to do it, so really, the first things first, before you go any further in this video isn't crucial to kind of the course, but it's an interesting thing to be able to see why integrating factors works. And I think if you want to really be in control of the mathematics of anything, it's always good to kind of go into why something works and get a really good idea, at least of the background of it, even if you don't understand it fully. Okay, so first things first, what I'm going to do is this at the moment is what's known as non-homogeneous. Okay, why is it non-homogeneous? Well, basically, when we write, with a differential equation, we'll have a function, in this case it's y, and it'll also be the derivative of its function as well. So in this case, we've only got the first derivative, so it's a first order differential equation. So when we write the function and its derivatives all together on one side, if the thing that we're left with on the right-hand side is non-zero, it's called non-homogeneous. Non-homogeneous, right? If the thing on the right-hand side is equal to 0, so if we have dy by dx plus p of x times y, and if the right-hand side then is equal to 0, we call that homogeneous. All right, so if the right-hand side is not equal to 0, then we call it non-homogeneous. If it is equal to 0, then we call it homogeneous, okay, when we get all the function its derivatives and stuff on the left-hand side, or on one side, okay? So first of all, I'm going to look at this homogeneous case. So literally, I've just taken this, and I'm looking at the homogeneous case. So in other words, the case when the right-hand side is equal to 0. And I'm going to look at what happens with this case. Okay, so this is actually really nice and easy to solve because I haven't got a constant that kind of comes along for the ride. So I can actually solve it by a method of variation of parameters. Okay. So what I'm going to do is very much a bit like separation of variables, except it's not strictly separation of variables because I've got a variable coefficient here, but we can stick with that. So I'll end up with dy by dx, okay, is equal to, I'll just take this thing onto the right hand side, so minus p of x times y, okay, and then I just get everything involving y on one side and everything which is kind of a constant involving x on the right hand side. Okay, so I'm going to end up with, if I get rid of this y on this side, I'm going to have to divide by y, so I'll end up with 1 over y times dy by dx equals minus p of x. Equals minus p of x. And then if I want to get rid of this dx here, because this isn't involving y, I'm just going to have to multiply through by dx. Okay, and then I'll just integrate both sides like that. Okay, and then I just integrate those things, so I'll end up with here, with the integration of 1 over y with respect to y, I'll end up with natural logarithm of y, okay, and that's going to be equal to, well, just going to be the right hand side, okay, but I'm going to actually put the integration constant, which comes out of this when I've integrated this 1 over y, I'm going to actually put it on the right hand side, okay, so I'm going to put plus c1 here. All right, and then I can just rewrite this y explicitly, so get y equals on its own, so y equals e, and then it'll just be to this power, so to the integral of minus p of x dx plus c1, okay. Well, this is just the same as, because I'm adding powers together, this is just the same as times e to the c1, right, because if I then, because I've got the same base, therefore, I can just add the powers together and just combine it into the same thing which I had before. Okay, and I'm actually going to call that thing there, I'm just going to call that, say, C. Okay, I'm going to call that C. I'll just move that over. I'm just going to call that C, so instead of being C, and I'm actually going to call it, I'm actually going to say that constant there will depend on x. Okay, that constant will depend on x, because if you think that constant has come out of integrating this 1 over y with respect to y. So therefore, the constant which comes out will be dependent on my other variable. Okay, maybe you might want to think about that a little bit, but essentially it will be dependent on my other variable. Okay, in general, we don't normally write the dependency on x, but in this case, we have to write the dependency on x if it's going to work. Okay, that's the short answer for it. Strictly speaking, we should write constants dependent on x because it's a function. Okay, so this is what we've got. Okay, this is what we've got. So we've now got y, which of course is a function of x anyway. Y is equal to c of x times e to the integral of the minus the coefficient in front of the y dx, and that is the solution. That is the solution to the homogeneous part. Okay, homogeneous solution. Right. So in other words, what we've got is a solution to this thing here. The solution to this thing here is that. Okay, effectively in general terms. Right. So now, if we want to find the solution to the non-homogeneous part, so remember what the non-homogeneous part was. It was dy, let's go to that, dy by dx plus p of x times y, and that's going to be equal to q of x. So the solution to that will be using the homogeneous part. So in other words, we're going to be using this homogeneous solution, and if we plug it back in here, it should look something like that. It should look something roughly the same. So if we just plug it back in, we'll end up with a derivative with respect to y. Well, first of all, we can just plug this back in directly, okay, for y. But we need to find out what the derivative of this thing is. We need to find out what the derivative of this solution is in order to plug it in for dy by dx. So in other words, we can plug this thing in directly for y, okay, but in order to plug it into dy by dx, we need to find out what the derivative is. So what is the derivative of this thing? So then we can plug it back in. So what is the derivative of this thing here? Well, it's going to be the derivative of, it's going to be the chain rule, okay? Sorry, not the chain rule, the product rule. Because we've got something which is a function which is dependent on x. That's why we made this constant dependent on x, right? This constant is dependent on x. Okay, so that's going to be one function. And then this thing here is dependent on x. Get rid of that. This thing here is dependent on x. So therefore, we've got two functions which depend on x. So therefore, we're going to have to use the chain rule, the product rule, sorry. So it's going to be the first thing differentiated with respect to x. That's c dash x. So the c of x differentiated goes to c dash x. The other thing left alone. Okay, minus, actually I'm going to stick the minus out the front there, just for neatness, p of x dx, okay, plus the first thing left alone, which is the c of x, times the derivative of this thing. Okay, well, what's the derivative of this thing going to be? Well, it's, if you remember with, e to some function, what's the derivative of that? Well, it's going to be, the derivative of that is the derivative of the power, so f dash x, times just this thing alone, e to the f of x. Yeah. So in other words, the derivative of this second thing here, okay, is going to be the derivative of the power. Well, the derivative of the power, if this is the integral of minus p of x dx, and the derivative of that is just going to be minus p of x, right? So we're going to end up with a minus here. If we stick the minus here, p of x. Yeah, that's the derivative of this power here, okay, times this power left alone. Okay, so e to the minus integral of p of x dx. Okay, so that is basically the derivative of that. So then we plug it back into this original non-homogeneous equation. Okay, we plug it back in. What have we got? So we got this, so we get c dash x e to the minus integral of p of x dx, okay, minus c of x p of x e to the minus integral of p of x dx, okay, plus, okay, so that's basically what I've just written down there is just dy by dx bit. So I need to plus, okay, plus, I'll write it underneath, plus p of x times y, which remember y was this thing here, okay, so y, c of x e to the minus integral p of x dx, okay, and that is all equal to q of x, okay. Well, let's look at what we've got here. We've got a p of x, c of x, e to the minus, e to the minus integral of p of x d of x, we've also got that thing there. Yeah, so effectively those two things are going to cancel. We've got the same thing, one's being added, one's being subtracted, one's being added, one's being subtracted, so therefore those two things are going to cancel. So what we're going to end up with, we're going to end up with c dash of x e to the minus integral p of x dx. Okay, those two things cancel, so we're just going to left with q of x on the right hand side. Okay, q of x on the right hand side. So what does that mean? What does that mean? Well, if I rewrite c dash x in kind of our familiar way that we're used to, so dc by dx, so that's just c dash of x rewritten like that. Okay, c dash is just going to be dc with respect to x. Okay, and I've got e to the minus integral p of x dx equals q of x still. Haven't changed anything there. Okay, well, if I just get that thing on its own, so the derivative of my constant with respect to x on its own, then I'm going to have to divide by that thing. Okay, I'm going to have to divide by that thing. So therefore, that implies that dc by dx is going to be equal to q of x. Okay, well, look here. Let's look at what this actually means. Because I've got a minus here, that effectively means that, you know, it's a bit like saying 2 to the minus 1 is just going to be 1 over 2 to the 1. Okay, so the minus thing here basically means that what I should have here is actually 1 over that thing. 1 over that thing. Okay, I should have 1 over that thing. Right, so effectively what I'm going to be doing is if I'm multiplying through, right? So this should just be times e to the integral of p of x dx. Yeah? Okay, hopefully that makes sense. What I've just purely done is I've just seen that minus there, and I've just rewritten, before I've done anything, I've just rewritten that as this thing here. Okay, is this thing here, and so therefore to kind of isolate the dc by dx on its own, I'm just going to have to multiply through by this denominator. Okay, so that's how I've got to there. Okay, so therefore, what does that mean? Well, c then is just going to be the integral of all of this thing. It's just going to be the integral of all this thing, because if the derivative of c is equal to this thing, then c itself is just going to be the integral of this thing. So q of x e to the integral of p of x dx. Okay, and it'll also be plus a constant of integration. So this is with respect to x. And it'll also be a constant of integration which hangs around at the end. So I'm going to call this one c2, say. Another constant of integration there. Okay, and so therefore now I've got this c. Right, I can go back and find what I had up here. So this is y. Okay, y is equal to this thing. Okay, well, I now know what this constant here is. And I know what this c here is. Okay, because I've just found that out. So in other words, I had y is equal to c e to the minus integral of p of x dx. Okay, well, now I know what c is. This is what I end up with. So I end up with the integral q of x e to the integral of p of x dx, okay, plus some constant of integration. And then this thing here, I'm just going to rewrite this thing again. I'm just going to take note of the minus there. So I'm going to write it as 1 over e to that thing, e to the integral of p of x dx, okay? And therefore, that is what I end up with. So literally, I've just replaced c with that, yeah, with that in that box, okay? And so therefore, this is what I end up with here, okay? So this is what y is. This is my general solution for y, okay? And this is my general solution in my original equation. So, you know, what I had originally was dy by dx plus p of x y equals q of x. Okay, so effectively this is the solution for y. And if you compare that with what we do with the integrating factor, that is exactly the same thing, except the integrating factor kind of skips all that proof and effectively just says, okay, let mu equal this thing here. So in other words, let mu equal that. Okay, and that. Okay, and therefore that's exactly the same thing. Yeah, that is exactly the same thing. So in other words, mu, by letting mu equal e to the integral of p of x, so my constant here, with respect to x, then therefore that automatically just gets the solution out automatically. So that's the reason why the integrating factor works. Hopefully you followed that. I really encourage you actually just to go through the algebra. If you didn't quite follow that, it's just algebra. Okay, I've shown you all the steps. You can obviously refer back to this video if you need a reminder of kind of the steps or anything. But I really recommend you just go through and sort of find, do the algebra yourself, and then you can kind of really be in control of this thing.